Okay, let's return to our Framingham heart study, and here we have a 2 by 2 table that looks at the relationship between diabetic status, yes, no, at exam 1, and the sex of the respondent at exam 1. So what we got is we got that there were 4,434, there's our old friend, 4,434 individuals, of whom 121, or 2.73, remember, had diabetes, 2.73%, because I asked for the column totals. That means 97.27% did not. Now, how did this distribute itself amongst the two sexes? And the answer is, well, the overall was 97.27. For females it was 97.51. For males it was 96.97. So it's not too different from the overall. And there were 2.49% prevalence in females and 3.03% prevalence in the males. And so it doesn't look like there's any relationship between the sex of the respondent and whether the person had diabetes or not. And indeed, if we looked at the chi-squared, the p-value is 0.269, so there's no reason to believe with these data that we should reject the null hypothesis that the row and column classifications are independent of each other. Okay, so that's fine. That's 2 by 2. But the nice thing about the chi-squared test is that we can extend it to more than 2 by 2 tables. In fact, we can extend it to, as we say in the jargon, R by C tables. So any number of rows and any number of columns. So for example, if we extend this very same example, but extend it to, instead of looking at the diabetic status at exam 1, let's look at it at exam 3. So what do we have at exam 3? So here we go, we're asking diabetes 3, and same with the sex 1, and chi-squared and col. And what do we get for the chi-squared? We get that the p-value is 0.112. So we don't reject the null hypothesis that by the time they did the exam 3, that these two are independent of each other. But remember, what did I tell you? I said, be careful with longitudinal studies. Are we comparing the same group here as we did on the previous slide when we had diabetes 1? Is this the same group? And the answer is, well, we've got 3,263 here. How many did we have before? We had our old friend 4,434. So we've lost 1,200 or so people. We've lost a considerable number of people. Now, is there any relationship between, let's say, between the diabetic status and whether they didn't show up for exam 3? Or let's say between sex and whether they didn't show up for exam 3? Well, let's ask for, what about the missings? So if we ask for miss, we'll get the missings also in our tabulation. And there we have it. There are the 1,171 missing. Now, look what's happening. There is a 4% differential between the male missing and the female missing. In fact, if we look at the distribution down here and compare it to the distribution of there, it looks like there's a difference. There's the p-value is 0.003. So we would reject, the chi-squared test is telling us to reject the null hypothesis that the row classification and the column classification are independent of each other. If we tab plot this, there we see it. We see that these two plots, for males, for females, these two plots are not parallel to each other. This first component is bigger than that, And to make up for it, this component is bigger than that. So there's more males missing than females. Why? What's going on? I leave it for you to find out. I have no answer. But the statistics here is telling us that something may be going on that might be of interest. Here's another example. What this example is, another question that often comes up. How accurate are death certificates? So this study looked at 575 death certificates, and the row classification is whether the hospital that completed the death certificate was a community hospital or whether it was a teaching hospital. I believe this was in the state of Connecticut. Now, of these 575, 229 came from the community hospital and 346 came from the teaching hospitals. So roughly a third came from the community hospitals and 2/3 from the teaching hospitals, roughly. Now, what they did with these 575 death certificates is they went and compared each one of them to the medical records, and they checked to see if there were any inaccuracies. Now, they found that of 425 of them, of the 575, they were accurate. There was no inaccuracy. So that was great. Then where there was an inaccuracy, they classified that as either the green column, which is there was an inaccuracy, but it wasn't that bad, so there was no change. It didn't require a change, and there were 62 like that. But then there were 88 of them where the mistake was egregious enough so that they had to recode and they had to resubmit the death certificate. Now, the null hypothesis is that it doesn't matter. The row classification is independent of the column classification. That means that, remember we said this was 229 over 575 is roughly a third. So that means that take these 88, roughly a third of them should go up here and a third of them should come down here. Take these 62, roughly a third of them, a third should be up there and 2/3 should be here. And take these 425, roughly a third should be up there and 2/3 should be down here. That's what we would expect to see. Now, if we look at the tab plot for this, we could either do it with the status as the percentage. So given the status, so given the accurates, how does that divvy up between the teaching hospitals and the community hospitals? And we see that this is much bigger than that. This is much bigger than that, but this goes the other way. So with the recoding, we're getting a different pattern than the no change status and the accuracy status. Okay, so it doesn't look like this for the community hospitals is parallel to this. In fact, let me remove that. So is this set of 3 bars giving you the same picture as these set of 3 bars? And the answer is no. Look at this one. This is the biggest. The biggest is here. The biggest component is there. Now, we could have done it instead of status, we could have done it by hospital. So here it is by hospital. And we get the same picture. With the community hospitals, we get a much bigger distribution down here than we do with the teaching hospitals. So this looks mighty suspicious. And in fact, when we submit this to Stata, we get that the p-value is 0.001. That's telling us that when we compare this to that, 18 to the 24.7, 54 to the 35, 268, and compare that to 255.7, when we compare what we actually observed to what we expect to see if there is no relationship between the row and column classifications, then the value we get is much bigger than we would expect purely by chance, and the p-value is there, less than 0.005. So we would reject this null hypothesis at the 0.05 level. And that is how we test an R by C. It's a simple extension of the 2x2 table. Except, remember, we don't do a continuity correction. We only do that with the 2 by 2 tables.